This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 6, Chillers and Condensers. A chiller makes chilled water, and everything it pulls out of that water, plus the work the compressor adds, has to be rejected at the condenser. How you reject it, to a cooling tower, to outdoor air, or through a VRF system, sets the machine's efficiency. We'll size the condensing water flow for a water-cooled condenser, then rate a machine with EER and COP. Concept 1. Where the heat goes. The refrigeration cycle itself is week 3 material. Here the component that matters is the condenser, the piece that dumps the rejected heat. 3 arrangements dominate. Water-cooled sends the heat to a cooling tower, rejecting toward the wet bulb, the coldest condensing, the best efficiency, and the only one with a printed sizing formula. Air-cooled uses a finned coil straight to outdoor dry bulb air. Simplest, no tower, but warmer condensing and lower efficiency. And VRF, variable refrigerant flow, modulates compressor speed to match part load. Concept: the heat rejection balance. Energy in equals energy out. The refrigerant carries away the evaporator load, and the compressor adds its work as still more heat. Both have to leave at the condenser, so condenser heat rejection equals the cooling load plus the compressor work. That means the heat leaving the condenser always exceeds the cooling load delivered to the building. The ratio of the two is the heat rejection factor, and it is always greater than 1. Setup: the water-cooled condensing water flow. The condenser water absorbs the rejected heat as it rises from inlet to outlet temperature. So write the sensible heat balance and solve it for volumetric flow. Heat rejection over the water's volumetric heat capacity times the temperature rise. Our case rejects 150,000 BTU per hour with a 10-degree condenser water rise. 2 cautions: size on the condenser rejection, not the chiller's cooling load, and remember the formula returns cubic feet per hour. The handbook also prints a tube-side pressure drop relation alongside it. Solve. Divide the heat rejection by the water's volumetric heat capacity and the 10-degree rise, and the flow is 240 cubic feet per hour. Multiply by the handbook's conversion factor, 0.125, and that is 30 GPM. Sanity check, that is close to the familiar 3 GPM per ton of heat rejection at a 10-degree condenser water rise. Concept: rating the machine. 2 ratings compare the cooling delivered against the electrical power drawn, and they differ only in units. EER divides cooling in BTU per hour by the raw watts drawn, so it carries units of BTU per hour per watt. COP divides the same capacity by watts times 3.412, which converts those watts into BTU per hour. So COP comes out dimensionless. Because that factor is the only difference, COP equals EER over 3.412, and it is always the smaller number. Solve. An air-cooled packaged machine. Capacity is 120,000 BTU per hour, and it draws 10 kilowatts, which is 10,000 watts. Capacity over the raw watts gives an EER of 12. Divide instead by watts times 3.412, and COP is 3.52. And 12 over that same factor checks to 3.52 as well. A water-cooled chiller on the same duty, rejecting toward the wet bulb, would land near a CRP of 5 to 6. Concept: comparing the 3. The efficiency gap is really a condensing temperature story. Water-cooled rejects toward the wet bulb through the tower. The tightest approach, the coldest condensing, the highest COP, but it costs you a tower, a condenser water pump, and water treatment. Air-cooled rejects to the dry bulb, which is always warmer than the wet bulb, so condensing runs higher and COP lower. In exchange, there is no tower and the system is far simpler. VRF modulates refrigerant flow to track the load, so it is strongest at part load where fixed-speed machines just cycle. The cycle, the ton, and COP fundamentals are back in week 3. Traps. 4 ways this bites. 1. EER versus COP. EER divides by raw watts, COP by watts times 3.412. Hand back the wrong one and you are off by that factor. 2. The condenser rejects more than the cooling load. Our 120,000 BTU per hour unit drawing 10 kilowatts rejects about 154,000. Size the condenser on that, not on the capacity. 3. A tower rejects toward the wet bulb, an air-cooled coil to the warmer dry bulb. Cooler condensing is the entire efficiency case. 4. The flow formula gives cubic feet per hour, multiply by 0.125. Reading 240 as GPM is an 8-fold error. Quick recall. Condenser heat rejection is the evaporator load plus the compressor work. So the heat rejection factor sits above 1. Condensing water flow is that rejection over the water's volumetric heat capacity times the temperature rise, in cubic feet per hour, times 0.125 for GPM. EER is BTU per hour per watt. COP is the same capacity over watts times 3.412, which is EER over that factor. Golden rule, size the condenser on load plus work and keep the two ratings straight by 3.412. Next up, Lesson 7, Heat Pumps and Thermal Storage. A heat pump is just a refrigeration cycle run for its useful heat. Same hardware, rated by COP as heat delivered over work in, and measured against the reversed Carnot ceiling. Lesson 7 sets that alongside thermal storage, shifting cooling production off-peak with ice or chilled water tanks. Everything's at PEPrepengine.com. Cheat sheet, worked solutions, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.